All right, this is lesson 7.5, interpret exponential word problems. We've got two objectives here. You should be able to write exponential expressions that model a real-world relationship. You should also be able to interpret the meaning of coefficients of exponential functions in terms of real-world relationships they model. A factor, we should know what a factor is. It's something that is being multiplied by another factor. In fact, we also talked about a growth factor or a decay factor when we saw exponential functions. So here's an exponential function. It might look more like this, like f of x or something. But you should know that a is our starting point. It's sometimes called our initial value or our y-intercept. And r, that's our factor. That's this factor here. It could be a growth factor if it's bigger than 1. It could be a decay factor if it's less than 1. But that's our factor. And one thing I want to remind you of is that if we're talking about percentages, then our factor is going to be 100% of what we started with, plus or minus, depending on if you're growing or decaying, the percent that you're growing or shrinking by. If that doesn't make sense, I will explain it some more in this example below. So here's our example word problem. We have a certain type of bacteria, and it's starting with a population of 100, growing at 5% every hour. It's asking us to write a function that gives the bacteria population, P of t, on the reservation of t hours from now. Okay? We can do that. So first off, I see some numbers that it gave us. 100, I see 5%. First thing we need to do is determine, okay, which one's A, which one's our starting point, and which one's R, our factor. Hopefully, you see that our starting point is 100, A is 100, and if we're growing by 5%, that means our factor, R, is going to be 100% plus, because we're growing, 5% more. And 5% as a decimal is 0.05. So we can add those together. R is going to be 1.05. All that's left to do is write it in function form. We'll use P of t instead of f of x though. So we'll have P of t, the population of the bacteria, t hours from now, is going to be A, which we know is 100, times R, which we know is 1.05, and instead of x, we're just going to use t. So to the power of t, the variable goes in the exponent. That's our function. Let's try one more. We'll write a function to model this word problem. So it says you deposit $250 in a savings account, and it grows by a factor of 1.5 every month. Write a function that gives the total balance of the savings account S of t on the reservation of t months from now. So, which one's A, which one's R? That's our A, and this is our R. The nice thing about this is we don't have to add. This is not a percent. It's just telling us R is 1.5. So from there, we can write our function S that depends on t. It's going to be A times R to the power of t. There we go. I might ask you to go the other way. Instead of giving you a word problem and asking you to write a function, I might give you the function and ask you to interpret what it means. So the expression 2 times 1.5 to the power of t models the number of bacteria in a culture as a function of the number of hours since the culture was created. What does 2 mean? Well, in order to break this down, we have to remember that 2 is our A value. That's our starting point, our initial value, our y-intercept, whatever you want to call it. That's our starting point. And if we want to describe what the starting point means in this context, if we can do that, we're good. So all this means is 2 is the number of bacteria that we start with. You can say we started with 2 bacteria. All right, and then what does the 1.5 mean? Well, since 1.5 is where R is supposed to be our growth factor, if you can tell that 1.5 is the growth factor, then we just say the population of bacteria is growing. We know it's growing because 1.5 is bigger than 1. And then we need to say how fast it's growing. So you can say by a factor of 1.5. We do have to say how often, though. Is it growing by a factor of 1.5 every minute, every hour, every week, every year? So we need to read that word problem again carefully. It's saying that T is the number of hours since the culture was created. So it's growing by a factor of 1.5 every hour. If you wanted to, you could replace the growing by a factor of, you could say it's growing by 50%. So you take out by a factor of 1.5 and you could say it's growing by 50% every hour. Either way is fine, whichever you prefer. We do have one more question here. How much bacteria is in the culture after 5 hours? So it called it an expression, which that's true. There's no equal sign, so this is an expression. But it's kind of bothering me that this isn't written as a function. So let's name this expression B of T. So B for bacteria. This is the number of bacteria at time T in hours. Now we have a function, and it's giving us 5 here. So let's plug in 5 for T and see what we get. We'll have 2 times 1.5 to the 5th power. And if we plug that in to our calculator, we should get 15.18, blah, blah, blah. Again, just like we did in the last video, we're going to choose to truncate rather than round. We'll get the same answer either way here because 15.1 rounds down, but we're just going to say this is 15 bacteria. So there's 15 bacteria in the culture after 5 hours. All right, last one. Gives us an expression here, and right off the bat, you should be able to pick out A and R. That expression models the per capita gross domestic product, or GDP, of the United States in thousands of dollars as a function of the number of years since 1950. So, because it's saying since 1950, let's make a note here. Let's just call that T equals 0. So in 1950, that's 0 years since 1950. But I'm skipping ahead a little bit. In 1954, that's how many years since 1950? Well, it's 4 years after 1950. So T would be 4 for that problem. All right, let's go back to where we were. What does 8 represent in the function? So 8 is our A value. That's our starting value. That means we start with 8. Is that $8? Oh wait, no, it's not because it's measured in thousands of dollars. So $8,000. Really, I should probably be more specific. I would probably accept this, but instead of we start with, it should say the per capita GDP of the United States was $8,000 in 1950. But as long as you can communicate that's your starting point, that's good. All right, the 1.022, that's our R. That's our factor, and because 1.022 is bigger than 1, this is our growth factor. So we can interpret this as the per capita GDP. You can write it out if you want. I'm just going to abbreviate. Of the United States grows by a factor of 1.022 each year. And again, if you'd rather, I'll do it in purple, some different color, you could say it grows by, well, if we take 100% away, this is 2.2% more. It's 0.02, oh, I guess here, 0. That's our growth factor. That's 1 plus 0.022. And this, as a percentage, is 2.2%. So you could say it's, if you want to phrase it in terms of percent, you could say it's growing by 2.2% each year. All right, and the last question, what was the GDP in 1954? Well, again, we'll take that expression. I'm going to write it as a function instead. We could say G for GDP as a function of time, T. And then let's plug in 4. 4 years after 1950 would be 1954. We can take 8 times 1.022 to the power of 4. And when we plug that into our calculator, we should get about 8.72757. Now you might be wondering, wait a minute, how come we're putting so many numbers after the decimal here, but we didn't in the last problem? Well, that's because this number here is in thousands of dollars, right? But we don't usually write it as 8 point whatever $1,000. We can call this, we move the decimal over, that's $8,727.57. So our GDP in 1954, or I'm sorry, our per capita GDP in 1954 was about $8,727.57. All right, and that's it for 7.5. As always, ask a question or make up your own, and I'll see you all in class.